Alright, in this video we're going to look at ionic radii and how the size changes for different ions. Okay, so the first we're looking at here is when an atom loses an electron, what its charge is. So think about how many protons and how many electrons that would have. Well, if an atom loses an electron, you're going to think about like how I kind of have it written here. If I have 11 positives and 11 negatives, I lose an electron, I'm still going to have 11 positives, but now I have 10 negatives. So I have one extra positive compared to my negative. So that makes it a positive. So you can't think about when an atom loses an electron, it's not going to be a negative, it'll actually be a positive. So I would write that as something like Na+. A positive sign meaning that you have lost that electron. So with the size here, so we're talking about the same element, okay, we're not changing elements, the same element. Alright, what happens to the positive ion's radius? We call positive ions cations. So this Na+, we call that a cation. And then we're going to look at why. It actually does get smaller because actually there are more protons to pull on less electrons. So each electron will actually feel more pull. Because instead of being 1 to 1 here, where we look at 11 to 11, now I'm over 1 to 1. I have more protons for every electron that I have there. So instead of having just one pulling on one, you can think of it that way, now I've got, I don't know, you can say 1.5 pulling on one. It would happen again if I would lose another one. So if I would have 11 positives and 9 negatives to make a 2+ ion, it would be even smaller because now I have still the same number of positives but even less negatives for those positives to pull on. So each positive can pull on the negatives more. All right, now if we go the opposite way, okay, when an atom gains an electron, it's going to become negative. So I'm going to deal with something like F and a minus. Alright, its charge will be negative because I have maybe say 11 positives, now I'm going to have 11 negatives. Then I have 11 positives, now I've got 12 negatives. So now I have more negatives than I do positives, so my ion is negative. Okay, what happens to these ion radius? Okay, they actually become larger. Why are they larger? Because now there are too many electrons for my protons to handle. So the electrons don't feel as much pull because the positives are having a harder time pulling on all of them. Because I have 11 of these positives, and now they've got 12 they've got to control. Okay, think of it, they've got a bigger class now, and now they've got to control all 12 of these electrons. They can't all pull on them very well. So it actually gets larger. So positive ions do get smaller, negative ions tend to get larger. Okay, and that's within the same element. Right? We're not comparing F- to Cl- to I-. Okay, we're talking about F compared to F- or F compared to F+ to F-. Okay? Now, we're going to use these for the next few chapters. Okay? Which type of elements lose electrons? Actually, we're going to look at that metals tend to lose electrons. And what type of elements gain electrons? Those are going to be nonmetals. So metals tend to form cations, nonmetals tend to form anions. And that has to do with your ionization energy. Okay? If you've got a lower ionization energy, and that's the energy needed to remove an electron, you're going to tend to want to lose them. If it's easy for it to lose, if it's going to think, take my electron, it doesn't really bother me any, I don't really want it anyway, okay, it's going to be a positive. If it thinks, no, I actually would rather take somebody else's electron, okay, it's not going to want to lose what it has. Okay, we're going to work through these here in a minute. So I read the noble gas notation for sodium. Okay, sodium is Ne3S1. Has 11 electrons. Okay, Ne is that previous noble gas. So if I look at it there, okay, Ne is a previous noble gas, but there's sodium with its 11th electron there. It's going to be the third row. It's 3S1. All right. So the reason we do these noble gas notations is because it helps tell us where the core electrons are. Okay, when it helps us where the core electrons are, the rest of that stuff then is valence. So sodium has one valence electron. If I were, for example, had a different one, okay, so say we look at, let's do aluminum. So aluminum would also be Ne3S2, 3P1, okay, because it has 13 electrons. It would have 3 valence electrons, 2 in the S, 1 in the P. If it had 2 in the P, then it would be 4 valence electrons. Remember, this is what I said earlier, when you look at the ones based on what group it's in. So if you can see here, aluminum is in group 13, and it had 3 valence electrons. Right? Remember I said drop the tens place? Okay? You can also do it by writing out your noble gas configuration. That's an easy way to count as well. The ionization energy is the energy needed to remove an electron. So if I want to go ahead and take one of sodium's electrons, that's how much energy it would take for me to do that. Okay, so it's going to be a number. All right? So we're going to write the noble gas configuration for sodium after its first ionization energy. So that means, and write the ion that it would form. So that means that we're going to lose one electron. So if sodium has one valence there, the 3s1, it's going to lose one electron to look like just like neon. Now for right now, we're going to leave it like that. Normally you wouldn't write it like that, but for right now, we're just going to leave it. It's going to help us with this. Okay? We'd have 10 electrons, which looks like neon, even though it's not neon. Okay? It's Na with a plus. Still sodium, he just has less electrons than he had before. Now we're going to write the noble gas notation for sodium after its second ionization energy. So that means I've lost my second electron. So how much energy it would take to take my second electron? Okay? And my second electron, well look, I don't have any more valence there to take. So you got to take one out of its core. Okay? And so I'd have to have He, 2s2, 2p5, because Ne is the same thing as He, 2s2, 2p6. So I lost that end electron there. Okay? You always lose the ones on the outside first because they're further away. They're not held quite as tightly. Okay? So Na2 plus would look something like this. Well, Na2 plus doesn't actually occur. And we know that based on this chart here. Okay? Because a noble gas has a stable configuration of electrons as the energy level is full. They're on the end of the row. Okay? All elements want to have a full energy level and have an electron configuration similar to a noble gas. They share, lose, or gain electrons to do this. And that share, lose, or gain is what we're going to look at in the next 3 chapters. Well, right now we say, okay, sodium, why doesn't sodium lose 2? Well, we see the second ionization energy there for sodium is huge, okay, or at least it's big compared to what the first sodium ionization energy is, an IE ionization energy, okay? It jumps from 498 for that first electron to 4,500 for that second one. Okay, so if you look at the ionization energy chart and the noble gas notations on the previous page, why is sodium's second ionization energy so much larger? Well, if we look at the second ionization energy, that would mean you are taking one from its core electrons, which is part of neon. Okay, so it went from being something that had a full energy level, looking like neon, to now you want to take one from it. Well, it's very stable that way, so it takes a lot of energy for that to happen. And that works kind of where all of you see that little orange line where it changes. Those are kind of where you're changing from taking a valence electron from something to taking its core electrons, because you have that big jump, which is when you go along with that second question where it says, why is magnesium's jump in ionization energy from 2 to 3? So we're going to write the electron configuration. And so you see that neon is in brackets, and then you have 3s2. Well, magnesium is one that has 2 valence electrons. Okay, so it can very easily lose 2 of them, and that third one is part of the core and very hard to lose. So if we went back up and we looked at the one I wrote for aluminum up here, you have 3 valence electrons. So as you can see, when we look at aluminum, aluminum has 1, 2, 3 numbers that are fairly low, and then its fourth number is very large. Okay, so that, again, that line there is kind of where you are going from taking somebody's valence electron to taking their core electrons. If we look at phosphorus doesn't do this until 5, and so it can explain what type of ion it actually usually likes to form and why that jump isn't until 5. Well, phosphorus has 5 valence electrons. It's a nonmetal on the right side of the table. And it is actually easier for it to gain 3 electrons than lose 5. As phosphorus sits here, if it wants to look like argon, it only has to gain 3. But if it wants to look like neon and have 10, it's got to lose 5. It's kind of like it's easier to gain 3 than it is to lose 5 of them. That's why when we look at carbon and silicon that both have 4, they actually don't lose or gain electrons, they actually share. And that'll be a couple chapters later. Sodium's high reactivity to its ionization energy and what type of ion it likes to make. Said that metals like to be positive ions, that's what I have there, they make cations, because they have low ionization energies. Because they would much rather lose electrons than gain them to look like a noble gas. So sodium is very, very reactive because it only has to lose 1, okay, compared to something else that has to lose 2, or something else that has to lose 3. So you kind of think of it, the table kind of splits. The ones over here to the right we talked about for nonmetals are very reactive because they only have to gain a couple or 1 You look to the left side of your table, like beryllium. Beryllium has to lose 2, which is fairly easy for it to do. Okay, or potassium only has to lose 1, which is very easy for it to do, to look like a noble gas to be 18. When we look at these ions and what they like to form and how reactive they are, the easier it is for it to look like a noble gas, kind of the more reactive it's going to be. The last thing is we deal with D block electrons and nickel ions. Okay, so nickel, for example, is argon 4s2 3d8. Now, if you were actually to have nickel 2, it would actually be argon 3d8. Okay, the highest energy level is actually the 4th one. So you make sure the electrons are removed from the ion, or for the ion, that are from the highest energy level. They're not necessarily the ones that you add last, they're always the ones with the higher number. That's why you see no 4s2 there. Sometimes you'll see 4s0. That helps. Okay, but you don't lose the ones on the end. You always lose the ones with the highest number. We're talking about a D block.